Ladies and gentlemen, my name is Gaisin, and I am presenting today a joint work of the Karlsruhe Institute of Technology and Ulba Metallurgical plant on the characterization of intermetallic titanium beryllide. This material will be used in the blanket of a fusion reactor for neutron multiplication, and we believe it has much broader potential in other high temperature applications. For a long time, beryllium was considered the main candidate for neutron multiplication in fusion reactors due to its unique physical properties. However, metallic beryllium reacts strongly with steam and air, as shown here below. Under neutron irradiation, beryllium was intensively forming a very high porosity. But the addition of just one titanium atom to 12 beryllium atoms radically changes the structure and properties. This intermetallic compound, called titanium beryllide, has much higher operating temperatures due to better corrosion resistance and due to much lower swelling. Under the same irradiation conditions, beryllium looks like Swiss cheese in the left, and beryllide has almost no porosity in the right. Looking much closer to the material with TM, we always see large hexagonal bubbles in beryllium and only very small ones in beryllide. This also leads to significantly lower tritium retention in beryllide, which is important from a safety point of view, since tritium is a radioactive element. All these advantages of titanium beryllide allow it to change the blanket design. I will show you this in the next slide. This is a sector of the demo fusion reactor with a blanket model. In the previous design, the beryllium should be shaped like small 1 mm pebbles to withstand for the strong swelling and to facilitate the tritium release. This pebble bed concept is still not feasible for demo volumes, which requires 300 tons of beryllium pebbles, meaning thousands of machines running continuously for several years and producing pebbles one after another. The switching to a new material, to titanium beryllide, significantly changed the blanket design. Now, beryllide blocks should replace beryllium pebbles for neutron multiplication. Due to a higher packing factor, this design provides even a higher tritium breeding ratio. This means more fuel for the fusion reaction. The only problem was the lack of technology for the production of such hexagonal blocks from beryllides. The problem stems from the fact that titanium beryllide is a very hard and brittle material, comparable to gemstones. It has a complicated crystal structure with a limited number of slip systems, and its manufacture has faced many challenges. For example, conventional casting results in higher porosity and compositional shift due to perictetic reactions here. That is why we focused on powder metallurgy route. In the new technology developed in Ulba, pure beryllium and titanium powders are blended together and pressed at room temperatures to such tablets. During the following beryllide synthesis, these tablets swell intensively, forming a porous material with a low density. But this beryllide can be ground to titanium beryllide powder. And in the next step, vacuum hot pressing of this powder results in a solid, dense material, which can be machined to its final size and shape. At the moment, several blocks of titanium beryllide have been manufactured in industrial conditions using industrial equipment in the Ulba Metallurgical plant. They have hexagonal shape with a central hole. They are quite large, with 144 mm in diameter and 150 mm in height. The material has an almost single-phase titanium beryllide with only traces of beryllium and beryllium oxide. The material has a very low uranium content, which means there won't be long-lived isotopes after working in a fusion reactor. The obtained beryllide is a quite lightweight material with a density less than that of aluminium. Let's take a look at the microstructure. It consists of equiaxed grains. There are some particles within grains and at grain boundaries. There are no visible differences in the microstructure along and across the pressing direction. The mean grain size is measured as 6.5 microns. Electron backscatter diffraction showed that material is homogeneous without any microtexture. There are a number of grain boundaries with a 60-degree mesoritation associated with twinning. In the right image, the twins are highlighted in blue, and disregarding these twins, the grain size was determined as about 8 microns. This is quite small, taking into account a high pressing temperatures of 1250 degrees. Let's analyze what other phases are in the microstructure. Here you can see a triple junction with some small particles around. Some of them contain oxygen and do not contain titanium, which means that they are particles of beryllium oxide. At lower magnifications, larger dark areas can be detected, which are composed of beryllium, and this means that there was an excess of beryllium before beryllide synthesis. Titanium beryllide is a very hard material with about 1000 in Vickers. There are many cracks extending from the impression. They propagate both along grain boundaries and within grains. Using this equation and knowing the force, the crack length, elasticity modulus, and hardness, the fracture toughness was estimated at 2.4 megapascal to square meter. This value is common to many brittle materials such as intermetallics or ceramics. Titanium beryllide is considered a functional material for fusion reactors. Therefore, it does not have strict requirements for mechanical properties. However, this is of interest to the aerospace industry. 3-point bending tests were performed at room temperature. They did not show any significant difference between the two directions of testing, across or along vacuum hot pressing. The flexural strength is about 240 megapascal, and this is typical for beryllides. Compression tests of beryllides were carried out at room and elevated temperatures. Taking into account its low density, the material shows a very high compressive strength of about 2000 megapascal at room temperature and to about 1000 megapascal at 900 degrees. The material is brittle up to at least 900 degrees, at which the beryllide deformed plastically. The experiment is still ongoing and not yet completed. During the operation in a fusion reactor, the beryllide will experience pulses of rapid heating and cooling. To simulate this, the beryllide block was split to several pieces to form several current circuits for rapid induction heating. A water-cooled steel pressure tube was installed in the center hole for rapid cooling, and this picture shows how it looks during the thermal cycling in a chamber of induction furnace. And the next slide shows a typical one-day thermokinetic diagram with 7 heating cycles up to 920 degrees and rapid cooling between cycles to about 350 degrees. As a result, titanium beryllide did not fracture and there were no cracks on the surface. This means that the material can withstand at least 205 thermal cycles in a rapid heating cooling conditions. In the next step, we'll improve the setup configuration and increase the number of cycles to thousands. Thanks to these outstanding properties, low density, high strength, oxidation resistance, such beryllides can be used as high temperature materials for air and space applications, and we are open here for any cooperation. We hope to test our blocks in the ITER test blanket modules under neutron radiation in fast heating cooling conditions. We believe that the full potential of the material will be unfolded in demo and further fusion reactors. I thank you for your attention.